Hello friends, welcome to my channel, My Education Made Easy. In this video, we are going to discuss about orbits, spaceflight, and types of orbits. So here, if we see type of conic sections, what is the value of eccentricity, and what is the semi-major axis, and what is energy. So here, if we take any cone and if we cut it in different angles at different planes, we'll be able to obtain circle, ellipse, parabola, and hyperbola. That thing we'll be discussing in our this slide. So here we are going to take a cone in which if we cut it at exactly parallel to the ground, then we'll be able to see a circle. If we incline somewhat, then we'll be able to see an ellipse. If we cut it to the base of this cone, then we'll be able to see parabola. And then if we cut it vertically, then we'll be able to obtain hyperbola. This is how we are going to see these things. So here inside, from top view, if we see, inside we'll be able to see a circle, and outside we'll be able to see an ellipse, and then followed by parabola, and then followed by hyperbola. This is how we are going to form these things. So here if we go with sections, conic sections, so here in conic sections, if we go with circle, it will be having an eccentricity of E of 0, and semi-major axis will be equal to the radius, and energy will be less than 0. If we go with the next one, that is ellipse, so here the eccentricity lies between 0 and 1, and radius, that is a semi-major axis, will be greater than 0, and energy will be of less than 0. Similarly, parabola, eccentricity will be getting 1 for parabola, and semi-major axis will be of infinity, and energy will be of 0. Whereas if we go with the hyperbola, then we'll be able to see that eccentricity will be greater than 1, and we'll be having major axis, and major axis as less than 0, and energy as greater than 0. So here mostly we'll be dealing with circular orbits and as well as elliptical orbits. So in order to remember these things, for circle we'll be having radius as of same as semi-major axis. For ellipse we'll be having semi-major axis will be of greater than 0, and eccentricity lies in between 0 and 1. So next, already we have discussed this thing. So if we go with next thing, that is orbital elements. Before going to orbits and orbital types of orbits, we need to know some sort of orbital elements. So to mathematically describe an orbit, one must define 6 quantities called orbital elements. So here we are having total of 6 orbital elements. Okay, 6 quantities of orbital elements. So here we go with first one, that is semi-major axis. So here the semi-major axis is 1/2 of the major axis and represents satellite's mean distance from its primary. Okay, so here it is a minor axis and it is a major axis. Okay, so here we are going to state that semi-major axis is 1/2 of the major axis. So here this one is a major axis, and half of this will be considering it as semi-major axis. That means semi means half, major axis means half of major axis. That is semi-major axis, and it represents a satellite's mean distance from its primary. Okay. So with this, we'll be able to identify at what position the satellite is with respect to mean position. So in order to do that, we have taken these kind of points. So here we'll be having 2 focuses for an ellipse. So here from focus to any point on the ellipse we'll be considering, and again we are going to join this. So this distance will be of same wherever you go. This distance will remain same, that is a1 plus a2 is equal to b1 plus b2. Depending on this equation, we'll be able to identify where the object, where the satellite is revolving exactly. So here if we see, here we'll be able to see periapsis and apoapsis. So here farthest point we'll be calling it as periapsis, and nearest point we'll be calling it as apoapsis. And then here if we see, if we take our Earth, so here we'll be having north, here we'll be having an equator. So most of the geostationary orbits are with 0 angle to the equator. Okay, polar axis, polar orbits will be perpendicular to the equator, that is 0 degrees to the north, or you can say it as 90 degrees to the equator. So here I is nothing but inclination, W is nothing but argument of periapsis, and psi will be representing as a longitude of ascending nodes, and N1 is ascending node and N2 is descending node. So here N1 is an ascending node and N2 is an descending node. So here from N1 to N2 we are going to revolve. So here N1 is ascending and N2 is descending. So here this one is uh, satellite. Okay. So next quantity is inclination. Inclination is the angle distance between a satellite's orbital plane and the equator of its primary, or the elliptic plane in the case of heliocentric or sun-centered orbits. So here inclination is nothing but amount of inclination it is doing with respect to the equator. And then next one is prograde or direct. This is a terminology here. Out of 6 terminologies, this is also one. An inclination of 0 degree indicates an orbit about the primary's equator in the same direction as primary's rotation. A direction called prograde or direct. An inclination of 90 degrees indicates polar orbits. An inclination of 180 degrees indicates retro, retrograde equatorial orbit. A retrograde orbit is one in which satellite moves in direction opposite to the rotation of its primary. So here already have discussed. So here if it is making 0 degree angle with respect to equator, then we will be calling it as geostationary orbit. If it is making 90 degrees to this equator, that is parallel to the north pole and south pole, and then we'll be calling it as polar orbits. This is what we have mentioned here. So here we called a term prograde. Okay, so in the same primary rotation, if we are seeing it means, then we'll be calling it as prograde. Next term is nothing but periapsis and apoapsis. So periapsis is the point in an orbit closest to the primary. Okay, the opposite of periapsis is farthest point in an orbit is called apoapsis. Periapsis and apoapsis are usually modified to apply to the body being orbited, such as perihelion and apohelion for the Sun, perigee and apogee for Earth, perigee and apogee for Jupiter. So perilune and apollune for the Moon, etc. So here at start I will be getting PRI. Perigee means geo. Uh, Perihelion means loon means moon. So here similarly we'll be going with these things. Okay, then the argument of periapsis is the angular distance between the ascending node and the point of periapsis. The time of periapsis passage is the time in which satellite moves through its point of periapsis. Next one is a node. So here nodes are the points where an orbit crosses a plane, such as a satellite crossing the Earth's equatorial plane. Okay, and then if the satellite crosses the plane going from south to north, the node is ascending node, and if it is moving from north to south, then it is called descending node. So here it will define us the direction in which the satellite is moving. Next, the final thing is longitude of ascending node. So the longitude of the ascending node is the node's celestial longitude. Celestial longitude is analogous to longitude on Earth and is measured in degrees counterclockwise from zero with zero longitude, being in the direction of the vernal equinox. In general, three observations of an object in orbit are required to calculate 6 orbital elements. Two other quantities often used describing orbits are period and true anomaly. So here period P is length of time required for a satellite to complete one orbit. True anomaly, or V, is the angular distance of a point in an orbit past the point of periapsis measured in degrees. So here you can see there are 12 visible satellites. So here, depending on the inclination with respect to the equator, we can place 12 satellites in an visible range. And then, so here now we'll be moving or heading towards the types of orbits. For spacecraft to achieve Earth orbit, it must be launched to an elevation above the Earth's atmosphere and accelerated to orbital velocity. The most energy efficient orbit, that is, one that requires least amount of propellant, is a direct low inclination orbit. Okay. To achieve such an orbit, a spacecraft is launched in eastward direction from a site near the Earth's equator. The advantage of being that the rotational speed of Earth contributes to the spacecraft's final orbital speed. Okay, so here we are going to see that in order to achieve efficient orbit, we need to launch it from east direction because because of rotation of Earth will be able to achieve or take advantage of being accelerated to high speeds. At the United States launch site in Cape Canaveral, 28.5 degrees north altitude, a due east launch result in a free ride of 1,471 kilometers per hour, that is 914 miles per hour. Launching a spacecraft in a direction to the east or from the site far from the equator results in an orbit of higher inclination. Higher inclination orbits are less able to take advantage of initial speed provided by the Earth's rotation. Thus, the launch vehicle must provide a greater part or all of the energy required to attain orbital velocity. Although high inclination orbits are less energy efficient, they do have advantages over equatorial orbits for certain applications. Geo Geosynchronous orbit, or GEO, are circular orbits around Earth having a period of 24 hours. A geosynchronous orbit with an inclination of 0 degree is called geostationary orbit. Okay, so here this is already we have discussed, that is orbit with an inclination of 0 degrees is called a geostationary orbit with respect to the equator. Okay, a spacecraft in a geostationary orbit appears to hang motionless above one position on Earth's equator. For this reason, they ideal for some types of communication and meteorological satellites. A spacecraft in an inclined geosynchronous orbit will appear to follow a regular figure pattern in the sky once every orbit. To attain geosynchronous orbit, a spacecraft is first launched into an elliptical orbit with an apogee of 35,786 kilometers or 22,236 miles, called Geosynchronous Transfer Orbit (GTO). The orbit is then circularized by firing the spacecraft's engine at apogee. So there we are going to increase the amount of velocity once it is reached into an elliptical orbit. Then we are going to increase the velocity so that it will move towards the circular orbits. Polar orbits (PO) are orbits with an inclination of 90 degrees. Polar orbits are useful for satellites that carry out mapping and or surveillance operations because as the planet rotates, the spacecraft has access to virtually every point on the planet's surface. Then heading to walking orbits. An orbiting satellite is subjected to a great many gravitational influences. First, planets are not perfectly spherical and they have slightly uneven mass distribution. These fluctuations have an effect on spacecraft's trajectory. Also, the Sun, Moon, and planets contribute a gravitational influence on an orbiting satellite. With proper planning, it is possible to design an orbit which takes advantage of these influences to induce a precision in satellite's orbital plane. The resulting orbit is called walking orbit or precessing orbit. Next, move to Sun synchronous orbit or SSO or walking orbits. These are also walking orbits whose orbital plane precesses with the same period as the planet's solar orbit period. In such an orbit, a satellite crosses periapsis at about the same local time every orbit. This is useful if a satellite is carrying instruments which depends on a certain angle of solar illumination on the planet's surface. In order to maintain an exact synchronous timing, it may be necessary to conduct occasional propulsive maneuvers to adjust the orbit. Next, Molniya orbits. These are highly eccentric Earth orbits with a period of approximately 12 hours, that is, 2 revolutions it can take per day, and the orbital inclination is chosen so the rate of change of perigee is zero. Thus, both apogee and perigee can be maintained over a fixed altitude. This condition occurs at inclinations of 63.4 degrees and 116.6 degrees. For these orbits, the augments of perigee is typically placed in the southern hemisphere, so the satellite remains above the northern hemisphere near apogee for approximately 11 hours per orbit. This orientation can provide good ground coverage at high northern altitudes. Next, we'll be moving towards the orbital transfers. So here we are having a type of orbital transfer that is called Harman transfer orbits. Now, so here these are interplanetary trajectories whose advantage is that they consume the least possible amount of propellant. A Harman transfer orbit to an outer planet such as Mars is achieved by launching a spacecraft and accelerating it in the direction of Earth's revolution around the Sun until it breaks free of Earth's gravity and reaches a velocity which places it in Sun orbit with an aphelion equal to the orbit of the outer planet. Upon reaching its destination, the spacecraft must decelerate so that the planet's gravity can capture into the planetary orbit. So from Earth, if you want to launch a satellite onto the another planet, so here it comes. So initially, it has to escape from its gravitational pull and it has to enter into solar gravitational field. And after that, once it comes near to the planet, outer planet, in which to which we are going to set up a satellite. Once it comes into that gravitational field, it has to be decelerated so that it comes and get exactly placed in that particular outer planet orbit or destination planet orbit. Then this one will capture into a planetary. Gravity can capture into a planetary orbit. So here this how it works. So here first one is Earth's orbit. So into the Earth's orbit we are going to launch the satellite, and then once it reaches into Earth's orbit, it get accelerated so that it will go into the second stage, that is elliptical orbit, which is in third stage. In third stage, it will enter into the destination planet's orbit. Once it enters into the destination planet's orbit, there we are going to decelerate and then we are going to place that into that specified destination orbit. So here if you go with orbit types, mostly We can divide these things into three types, that is lower Earth orbit, medium Earth orbit, and geostationary Earth orbit, that is GEO, LEO, MEO, and GEO. So here, if we go with altitudes, lower Earth orbit will be at an altitude of 160 to 2000 kilometers from the Earth's surface, and this orbital time period will be of 87 to 127 minutes, and medium Earth orbits will be at an altitude of 2000 to 35,786 kilometers, and the time period taken for the orbital will be of 127 minutes to 24 hours. Next, we will be moving on to the final one, that is geostationary Earth orbit. That is at an altitude of about 35,786 kilometers. It will take approximately of 23 hours 56 minutes 4.1 seconds. So if we place any satellite in geostationary orbit, the satellite looks to be at the same point as Earth takes same amount of time to rotate around itself. Okay. So, whichever the satellite is there in geostationary Earth orbit, the satellite looks to be stable at a specified point in space. Next, we'll be heading towards Kepler's laws of planetary motion. Kepler proposed three basic laws of planetary motions. So, the first one is the orbit of smaller body about a larger body is always an ellipse with the center of mass of a larger body coinciding with one of the two foci of the ellipse. So here it simply states that whichever the planet is having a satellite, that satellite will be revolving around the specified planet in an elliptical manner, and that planet will be either of the two focus, either at one of the two focus points. So see here, if we take example, sun is at a focus, and here if we take this planet as Earth, then it will be revolving in an elliptical manner. Sun either will be over here or over be here. This is what his law is. Then next one, the orbit of a smaller body sweeps out equal areas in equal times. This is graphically depicted in figure where the areas A12 and A34 are equal if the time difference T2 minus T1 and T4 minus T3 are the same. So here at this particular point, if I consider at this uh, at this particular point, if I consider planet is there, and here near this point a satellite is revolving around it. So here if I join a thread from these two, this satellite in equal amount of time, it will sweep equal amount of area and it will move. So here technically here if we see at time t1 the satellite will be over here, and at t2 the satellite will be over here. Okay, T2 minus T1 is same as T3 minus T4. That means in equal amount of times we are going to take this amount of area which the satellite has covered. So here if we go with that, then here we'll be having area of 1 2, which is covered from time 1 to 2. For let example say from 1 hour to 2 hours, from 3 hours to 4 hours. So the time period will be of 1 hour for each, 1 hour for both, the same will be. And so the area covered in first 1 hour will be of A12, second 1 hour will be of A34. Okay, so these areas will be of same. E T1 T2 will be equal to E T3 T4, which is area 1 2 is equal to area 3 4. This is what the second law, in equal intervals of time it will cover equal amount of area, or it will sweep equal amount of area. Then the final Kepler's law, that is square of time period of revolution t of the smaller body is equal to the constant multiplied by third power of the semi-major axis length. That is here you can see that T square is equal to 4 pi square a cube by mu. Okay, so here time of the smaller body, so here square of the time period is equal to multiplied by third power of semi-major axis length. So here a cube is semi-major axis, so semi-major axis is nothing but half of the major axis length. If total axis length, if we consider it as 2a, then it will be of a. So here t square is directly proportional to a cube. We can say it as, or t square is equal to 4 pi square a cube divided by mu. So here we'll be moving towards the basic orbital equation. The centripetal force required to keep a particle with a mass m traveling on a circular path of radius r is given as Fc is equal to mv square by r, where v is the velocity of a particle. This equation can be partially derived intuitively by noting that if you swing a ball around your head on a string, if you increase the mass of the ball, you will have to pull harder on the string. If you swing the ball around your head at faster speed, you will have to pull much harder on the string. If you lengthen the string while keeping the speed of the ball constant, your tug on the string decreases. Equating this force and gravitational force, we get mv square by r is equal to gmm by r square. In this equation above, m is the mass of the object being orbited. Example, the sun, central object we can say it as, and small m is the mass of the object in orbit. Okay, at center, whichever the planet, whichever the body is there, that larger body mass will be considered at center, and smaller mass will be considered at outer surfaces. Okay, then capital R is the separation between the two objects, that is the length of the string. Rearranging this equation, we can get that V is equal to, upon cancelling small m on both sides and small 1 r on denominator, we'll be getting V is equal to square root of gm by r. Or we can take it as mass of larger objects can be given as V square r by g. Then where v is the orbital velocity of an object, g is universal gravitational constant, that is 6.673 into 10 power minus 11 Newton meter square per kg square. Me is mass of Earth, that is which is, we have neglected when upon comparing it with respect to the sun's mass, that is 5.98 into 10 power 24 kgs. And then r is the distance from the object to the center of the earth. These relations show that you can find the circular orbital velocity needed to launch a satellite into Earth's orbit, determine the mass of the planet or star or galaxy which has satellite with a known velocity and separation from the planet. Applying Newton's laws permits us to determine the mass of just about any structure in universe. So here, if we go with different types of orbitals, that is elliptical and circular orbital, the velocity value may vary. So here we can be given as square root of capital Gm of 2 by r minus 1 by a, which is for elliptical orbits. For circular orbits, it's v is equal to under root of capital G capital M by r. With this, I will be winding up the session. If you like the video, please do like, share, and subscribe. Thank you.